everyone. Welcome to the INTAREA session. Please take your seats. So welcome again. We are passing the blue sheets now. We have note taker. Carlos, thank you very much for that. Do we have a Jabber scribe? Can anyone help us with the Jabber? Jabber, someone please. We need to have a Jabber scribe if we need to get going. Can someone please give us a hand with that? So once again, we need someone to help us with the Jabber. Can someone give us a hand so that we can get started? There's a special seat for the Jabber scribe. You'll get goodies, cookies. No, seriously, guys, please give us a hand with the Jabber. We need to get going.
I'm definitely not the Jabber scribe, but someone's complaining on Jabber that the sound from your microphone is very poor.
Oh, okay. Well, it sounds quite loud here, no? Doesn't it? So
we had the same problem in another session this morning, so it's real. And the chairs ended up using that microphone next to you.
Okay.
I'll pretend to be a Jabber scribe.
Okay. Thanks for that.
I'll do a very minimum.
That's good enough. We'll get your cookie. Thank you. Exactly. So this is a note as usual, reminder of the IETF policy. So please, all of you be aware of what you say here, contribute, or otherwise express will be subject to the note As usual, minutes are taken. The meeting is being recorded. Your presence is being logged. Blue sheets are passing. Scribe, we have Carlos helping. If anyone else wants to help, please contribute online to the minutes on the Etherpad. The recordings and minutes will be public, and please make sure you sign the blue sheets. Now that we have blue sheets not taken in Jabber, let's move on to the agenda. So this is agenda that was posted last week and still hasn't moved. So we're going to give you a quick update on the status of the group as usual. Then we'll move for Eric presenting the provisioning domains. Vlad will be presenting remotely SOCs. Then we'll have a hybrid IC IPv6 from Luca, IP fragmentation considered fragile from Ron, limited domains and internet protocols from Brian, privacy issues, Eric, Nordmark, IP over Ethernet session held from Richard, and an update on the NAMS multiple access management service from Hanu. Does anyone have any questions or comments on the agenda? Okay, if none, then we're going to give you a quick update from the working group. Privacy considerations for IP broadcast and multicast protocol designers. We have another RFC published, so kudos to everyone. Thanks a lot for the comments and the good work on that publication. That's now RFC 8386. The IP tunnels in the internet architecture, it's actually expiring, and we have no update so far from the authors. I don't know if Mark is around. Apparently not, so we still have no update from the authors on that. The GUI, the generic UDP encapsulation draft, plus the GUI extensions, likewise has been sitting there for a while, and we have not heard a lot of feedback from the working group. Tom did a good job at responding to some of the questions. He did an update, but we need to have some more feedback from the working group. So please take a look at those drafts, and if you have any comments, since the drafts are pretty mature now, please let us know. It's important for us to have feedback from the working group on these two. And finally, we have the discovering provisioning domains and data from Eric, but we will hear his presentation. So moving on. Oh, sorry.
Thank you. Dave Simcoe from Ericsson, but with this hat on, I'm got the BBF liaison manager hat. There is a liaison from the broadband forum to the INT area that was sent out in the April timeframe, explaining that two things. One, they're starting work on a Yang model for ANCP, and the second, asking for progression of a draft that adds extensions to ANCP for new technology such as enhancements in DSL and G.fast. Now that draft has not been submitted, but I'd like to call the attention of the working group to that liaison so that they're prepared for when that draft gets submitted, so that we have some participation.
Thank you very much for that update. Yes, and please, whenever it's submitted, it would be nice to link it to the liaison so that people look at it with a good eye. I mean, I'm not sure everyone is aware of the letter.
Right. Okay.
So whenever
you want me to send the link to the list?
Exactly.
Okay.
Yes,
Thank you.
Thanks. Okay, so I guess next is Eric. Thank you. Oh, can you give it a try? Full screen. Yeah, super, thank you. So my name is Eric Ving from Cisco, and I'm presenting this draft that I'm co-authoring with Pierre, a colleague of mine, and Tommy Poli and Dennis Shinazi, and Wenshin Shao, with PhD student, postdoc student at Telecom Paris Tech. I won't explain the details of PVDs, as we explained it multiple times here. Just focus on the difference. If this thing wants to work, can you press? Sorry about it. So as you remember last time in London, we got IANA allocated and temporary code until reclaim of 21. That's a good thing. We got an extensive review from Tinchan, who is not here today, and from Zen Kao. I don't know Zen. If you are here, I'm happy to talk to you. We also get a design team lunch in London with some customers that were interested into PVD. And we are seeing, when we're talking about PVD here, it was explained it was a foundation work. It fixed one problem about the PVD, but you remember there is an extension mechanism where we can download a JSON file. And tomorrow at 9:30, Pierre will present a use case in the captive portal, so Tuesday morning. So it's really important work. Next. So what has changed in -02? Obviously, as we got now the IANA number, we put it there. A comment, I think it was raised by Eric Klein,
about the tendering herd effect. So we protected it, and I will spend more time on this. We were using, you remember, when we insert another routing advertisement header after the PVD option, because we want to change the value out of the routing header. We were using an A flag, like advertisement flag, but it's confusing because in PIO we also have an A flag, so we rename it into the R flag, telling route advertisement, not a big deal. Also, when we started the GAS01, the PVD was more a PVD ID option. There was only the fully qualified domain name, identifying basically the name or the ID of the provisioning domain. And as now it's actually more like a container, it makes no sense to call it a PVD ID option, and we simply call it PVD option, right? And before in GAS01, we were having a section about PVD aware host behavior. Obviously, we need to define the behavior with the new thing. But we also, as an information, explain what the non-PVD aware host will do. Meaning, people on implementation right now, if they receive a PVD, they will do that. Next. So that's basically the two things that has changed. The R flag, which is replace the A flag, and the delay. Some explanation about the delay, if you don't want to get. Next slide. Yeah, progress is not always progress, right? New stuff is not always something nicer. Okay, thank you. So the issue here is that you remember when some people need a host decide to fetch the new JSON file to get the new additional information. It's triggered by two things. It's triggered when it receives a route advertisement containing the PVD option with a sequence number which is different than the previous version. Now think about it. You are a big conference with 20,000 Wi-Fi clients, and suddenly you change the sequence number because you want to change DNS server or whatever. Do you think a TLS server will be happy to receive 20,000 SSL TLS connection at the same time? Most probably not, right? So we need basically to put some jitter there. And what we have decided is to use 4 bits, which is called the delay field. We take the value of this delay, so maximum 15 times 2, maximum 30, and we take 2 to the power of this number, which is up to 50 days. Okay, if you use the maximum value, is 50 days. And each and every host needs to wait a random time. So if it's something low priority, you put 50 days and you are solved. If you really want to solve quickly and you are ready to take the hit on the TLS server, you put 0, 1, and everything is updated in a matter of seconds. The other point, when we refresh the JSON file, if you don't use this sequence number mechanism, is that there's an expiration date in the JSON file when it needs to be refreshed. Simply, you do it before the expiration time and the time which is between now and the expiration time, basically. Okay, this is one way to solve it, and I think it's okay. Next. Implementation status, nothing has changed a lot there. The Linux kernel is improving, and we are in talk basically with the maintainers to, in a couple of weeks or months, upload our change there. The link is there if you want to try, and I'm more than happy to spend some time with you on this. Next. So, even after the review of Zen and Tim, we obviously welcome more reviews. Right, there are always more things in multiple ads and only 5 ads. I am presenting this on V6Ops on Thursday, just to give the opinion from the operational community. I was able to present it on 6 months today. And the authors feel in the draft doesn't change a lot anymore. It's basically fine-tuning, some wording change, and we got a couple of comments during lunchtime from Eric about some wording there and adding some more explanation. But I think when we meet again in Bangkok, we will go and ask for Antigua Pascal. Not now, but next time. Any question? Because I think it's the last one. Okay, so you're more than welcome anyway on Captive Portal tomorrow morning and on V6 Ops. Okay, thank you.
Sorry. Thanks a lot. Okay. So next we have Vlad, who is on Mythical, and then I think he has to request the queue. Excellent. There
Hi,
you
can
are.
you hear me? Can you hear me?
No, very, very, very low volume. Can you increase your volume somehow?
How about now?
Too loud.
Is this okay?
Good.
All right. Okay, so I'm going to talk about what we've been up to with regard to SOX version 6. So next slide,
Sorry,
please.
Vlad.
Say again?
Just a little lower. It's still saturating. If you don't mind.
Is it okay now?
Yes, thank you.
All right, no problem. So next slide, please. So most of the changes in the latest revision are based on our experience implementing it. So what that basically means is that whenever I run into something that I didn't want to code, I just change the draft. Now, all jokes aside, the latest revision gives implementers more freedom with regard to which functionality to implement and which to leave out. So salt options were removed because it turns out that we didn't have a use case for them after all. We've also renamed the socket options to stack options, but they still do roughly the same thing as before. So next slide, please. So the approach we took with options was that we tried to make all of them optional. So if all you want is a basic proxy, you can strip SOX version 6 all the way down to version 4 functionality. If you want to do authentication as in v5, you need to support authentication method options. Authentication data options are orthogonal to these and enable you to do zero-RTT authentication. So for example, username and password authentication works in zero-RTT mode without doing any kind of prior negotiation. Also, if you want to safely use TFO or TLS early data, you'll need idempotence options and some kind of authentication. So next slide, please. So we've also added a section that tells you when TFO is safe to use with SOX version 6. So as you may know, TFO payloads can be replayed under rare circumstances. Obviously, if the protocol running on top of SOX tolerates TFO, then it's okay to use TFO. Also, if the SYN only contains the request header and none of the initial data, then there's nothing for the SOX proxy to replace, so TFO is also safe. Now, TLS with early data is already safe to use on top of TFO, so there's no question about that. And if you haven't got any other kind of mitigating circumstances, idempotence options can make replays almost impossible. So next slide, please. So the idempotence mechanism has also received some attention. Now I'm going to give you a quick refresher about the mechanism. So after everything is set up, the client has a window of tokens to spend. In this case, the window contains tokens 1 through 100. The client spends the first token by placing an option in the request, in this case, token 1. Likewise, the proxy places an option in the reply, informing the client that the token was spent successfully, along with with an option informing that that the window was shifted past the spent tokens. So it's now all tokens 2 through 101. So next slide, please. So obviously, the main point of the mechanism is that a token can only be spent once. So in this case, if we try to spend token 1 twice, the second request won't go through. The mechanism also tolerates tokens received out of order. So in the figure to the left, spending token 2 does not cause the window to shift because token 1 is still pending. And as soon as token 1 is received, the window is shifted by 2. So next slide, please. All right. So in the previous version of the draft, the proxy sent out the window advertisement as soon as it honored the client's request. We've moved it to the authentication reply so that the proxy to server RTT has no impact on its timeliness. So next slide, please. The idempotence mechanism is also relatively lightweight. So the proxy only needs a fixed size bitmap in order to track the tokens in its window. So in our implementation, we handle drop requests by forcefully moving the window past unsent tokens if the latest token passes the so-called high watermark. So in this case, we have a window of 100 and a high watermark of 75. Requests run into our loss for whatever reason, and then the client keeps making requests. The proxy does not shift the window until token 75 is spent. When it decides that the high watermark has been passed, and it discards token 1. Token 76 again goes over the high watermark, causing the proxy to discard token 2 as well. Now token 2 was followed by a multitude of spent tokens, so the window was shifted all the way to 77. So next slide, please. So there is a corner case when it comes to idempotence options. Let's say that 2 duplicate requests hit the proxy for some reason. Obviously, the second one is rejected. So next slide, please. Now, if the proxy were to be restarted between the two, the second request would normally be rejected because the newly restarted proxy doesn't have a window associated with the client. Now, next slide. Now, what if the proxy after the restart has no support for idempotence options and simply ignores them? This is allowed under the current version of the draft. So what basically happens is that the duplicate request is honored again. This is not something that we want to happen. So next slide. So to mitigate this issue, the administrator could take some extra steps to prevent replays. So if the idempotence options were used to enable the blanket use of TFO, simply disabling TFO1 MSL before the proxy reset should be enough. The issues with TLS early data will simply go away if all the TLS sessions are killed right after the restart. So next slide, please. So now I'm going to give you a quick taste of our message library. So it has all the features in the draft, and we've written it in C++, but it also has C bindings. What you see on the screen is the C API. So in order to create a request, you simply fill out a structure describing what the request should do. So in this case, we're trying to connect to somesite.org on port 80. And we're also trying to use TFO. The structure has many fields, many other fields, but you simply leave them blank. So if you don't want to use them, then you simply call SXM request pack. And if the structure you filled out is okay and the buffer is large enough, you've got yourself a serialized request. And then you simply use whatever network API to send it over to the proxy. So on the proxy side, you simply receive a bunch of bytes, and then you and then you call SXM request parse. Now this will give you an error if you need to receive more of if that wasn't a complete request. You also receive an error if the request was invalid. And then you simply go about honoring the request, and then you can free the structure created by request parse. And that's about it for the API. The functions dealing with the other message types are very similar. So next slide, please. So so the feature complete message library is available on GitHub. We also have a utility library that implements all that's basically a motley crew of all kinds of stuff that we deem necessary for the development of SOC 6 apps. We've used these two libraries to implement a basic prototype based on shadow socks, but a full-blown implementation with most of the features in the draft is in the works. You can also find that on my GitHub page. And that's about it. I'll be happy to take questions.
Thanks a lot, Matt. Does anybody have any questions? Maybe? Yes. Hi, Ben Schwartz, Google. So, hello? I think, so I think this is very good work, and
Thanks.
I think it's a very interesting design. I think it's reasonably simple. One thing I would like to see is a little bit clearer warning about the UDP support, because although this draft has good support for using an encrypted transport for the TCP side of the communications, if you do use the UDP associate method, you'll lose the protection of that encryption layer. And in fact, if you don't need encryption, if you're running over a local on a local interface where encryption is not needed, then you also don't need SOC 6 actually, because you don't have any latency between your client and server. So I think that at a minimum, a warning about or possibly deprecation of the UDP associate command in SOC 6 might be reasonable.
Well, we have no plans to deprecate the UDP associate functionality. And in fact, if you need encryption, we plan to run it over DTLS, but we haven't gotten around to looking into it yet. So at the moment, I could write some text about UDP associate and also UDP associate over DTLS, but it would be mostly like armchair text.
Okay. Yes. If you foresee moving toward DTLS for those packets, then I think it's fine to keep it, provided we actually get there.
And by the way, DTLS and TLS is not mandatory, so you can also run SOC 6 over plain text over regular TCP.
Right. So I'll repeat something I've said earlier, which is all these latency optimizations are great, but latency optimizations only make sense over high latency networks, which are essentially always insecure unless actually secured by some mechanism. So, so I think that we should be strongly recommending using a secure transport in these cases where we are trying to reduce round trips.
All right. There's one other use case that we've thought about, and that is MPTCP deployment on mobile phones, and that we don't. That's a use case where you don't necessarily want security, but the latency between the mobile phones and the base stations can be quite high, and that's why we try to shave off as many RTTs as possible. So, I will make the case that the latency optimizations also make sense even if you're running over plain TCP.
So it seems to me that you're arguing that essentially the LTE link layer is actually a secured link.
No, I'm not saying that. I'm saying that you might simply use it in order to take advantage of MPTCP for your mobile phone. But you may not actually want any kind of security.
Okay, so
I mean, if you still want security, you can run it over TLS, but that's not mandatory.
okay, I'll just point out that just in the past week or two, there's been a new attack published called Alter, which points out that in fact LTE has mutable encryption for much of its security. So an attacker who's outside the cell network can modify the contents of packets. So if you think about evil things that somebody could do by mutating your SOC 6 commands, those are plausible attacks unless you actually have security on this link.
All right. I mean, that's certainly something to think about, but So the security side and the RTT optimizations are kind of orthogonal. So yeah.
Tommy Polly, Apple. So thank you for doing this. It's very interesting.
Thank you.
One comment on the usefulness of the latency optimizations. I think there are some cases in which you can get away without having this particular layer have its own security encryption that would still be useful for this. For example, if you're on a kind of like IoT style network in which you do have some very small pipe that is fairly slow but is otherwise protected that you're sending things over, then being able to proxy this information quickly would be very useful. So I think we shouldn't make it a must. It should be a should probably for the security. Then overall, I also wanted to see how this relates to some work that we're doing, like the TAPS Transport Services Area Group, looking at the some more generic APIs, kind of like what you're doing here, that allow you to do multipath and idempotent data and other things. So I'm just kind of pitching an offering of doing some working review on this, of trying to fit this protocol in as an implementation beneath that to see how well it fits into that type of API and give any feedback if it doesn't seem to align with what we're looking at there. We already, in our implementation, support SOX 5 and SOX 4, and we also independently support TLS and MPTCP, etc. So I think this would be a cool opportunity to try to put those all together into a proxy scenario and see how that works.
Well, yes, I'd be happy to see that happen.
Cool. Thanks a lot, Vlad. So we've had a couple of meetings discussing this draft, and there's interesting feedback from the group. We're wondering if we think this is something that the group is interested in adopting as a working group item, and we would like to get a sense from the room here. So all those who think this work is interesting, worth it for the group to adopt, please hum now. All those who think this is not interesting or should not be adopted, please hum now. Okay, so very mild, I guess. I don't know if you heard that, Vlad, but it was a very mild support for it. So I encourage you to please keep working on it and get support from the group and work integrating all the comments you've been hearing.
Sure.
Thanks. So
Thank you for having me.
thank you. I'll kick you out right now. Bye. Thanks. I like this button. So next is Luca for Highway ICN IPv6.
Hi everyone, so I'm Luca from Cisco. So today I'm going to present the IBICN. This is a network architecture to implement NB ICN networking on IPv6. And okay. Right, next. You say one slide. Because the motivation is something that I'll present in a second, but I'll show you a little bit about how we introduce this kind of new way to introduce location-independent communications in IPv6, which requires a number of modifications and interaction with special nodes in the network. A very high-level overview about the whole architecture and now the implication to the transport layer as well, and also how we plug new applications and existing applications on top of it. Next. So the motivation of this work is essentially to insert ICN in IPv6. with the philosophy to have an evolutionary implementation of it instead of a clean slate implementation. So it's something we can implement by introducing a few nodes in a network, by modifying the endpoints, introducing a new transport service on top of it. So the idea is to have a short time to deployment, minimize standardization effort, minimize with respect to the work that's currently done in ICNRG, for instance, and but also have a hybrid deployment, meaning that you can have for several use cases deployments where you need to introduce one node here and there to be able to get some of the advantages that you can have for this kind of architecture. Next, please. For those who are not familiar with ICN, I'm trying to summarize with very short the philosophy of ICN in the first place. So it's a network architecture that is supposed to transport any kind of application. So it's not for content distribution. It can transport real-time communication, can transport, just like IP, can be used to transport any kind of application. As I can show you in a second. The philosophy is to enable connectionless and location-independent communications by identifying data with unambiguous names. So it seems like high level, but this is what we're trying to do. And the basic semantics and core principle is that communication is a request reply down to the network layer, and every HICN nodes accept at a given interface a data packet only if there is a pending request for this data packet. So you cannot send data to an interface if there is no request pending for it. And so this is called local flow balance principle, which is a very important one for many reasons in ICN, so to be considered. The second component, third component, is what is called data-centered security. What I mean with that is, what we mean with that in ICN is that considering that the data is associated to a location-independent name, we need a way to associate the data producer to the data that the consumer is receiving. So the consumer and the producer are two endpoints in the communication, in the HICN architecture. The consumer is the endpoint that is fetching data, and the producer is the endpoint that is producing data. So the consumer must be able to authenticate in a location-independent way the origin of the data, so the producer. So which means that there are signatures that can be used by the producer to verify that the producer that assigned the data is actually the one expected by the consumer. Next slide, please. So how do we do that? So we introduce a second namespace in IPv6 by reusing v6 address to introduce these location-independent identifiers for data sources. So a data source can be an RTP media source, can be an HTTP service, a video object, a live channel, but can also be an endorsed or a service in general. So it's generic. So what is not? It's not an identifier of a network interface. In a very specific case, can also be that. Next. So the first component, the first thing we introduce is the concept of name prefix, name suffix, and name, and full name. So a name prefix is encoded as an IPv6 128 bits number, which is carried in IPv6 header fields. We're not sure where exactly, but it's you look at it, it's a v6 number, and they will use differently. The suffix is the piece of data that is used by the transport layer to encode segmentation information in a sequence of data. And so it's encoded in a layer 4 header. So the full name is a concatenation of these two numbers, and so what you get at the end is a number that can be used to index a single data packet with different scopes. Next slide, please. So if we use IPv6 numbers as data names and prefixes, we need to find a space, a new namespace. Like this could be a new address family, but can also be just an address block that is reused differently. So this is an open problem. Like it can also depend on the deployment, but this is something that must be considered, like which blocks you're going to use to do that. Next slide. So the packet format. Before I go into the detail of the packet format, as I said, the core semantics of the protocol is being request-reply, even in the network layer. So that means that we have two different protocol data units. One is the request, and the other one is the reply. So the request doesn't carry any payload, usually. And the reply is the piece of data that is actually carrying application data that is requested by the consumer endpoint. So we have these two protocol data units, and interest is actually the PDUs that is used to index the data packet. So it can be used to fetch the data, can be used to identify the data within a packet cache, and also in the transport endpoints to pull the data into the upper layers. So you can index the real payload thanks to this specific PDU packet. So for those who are familiar with the ICN, the semantics are unchanged with respect to main data network in CCN, just like as they are specified in this draft being worked out in the ISO working group. Next slide. So the packet header, so as I said, there are two PDUs. But if you look at the V6 header of these two different PDUs, you see the same thing. What you see is an IPv6 packet header. And the two things that we need to look at are the source address and the destination address in V6. For the request, we put the destination address field contain the name prefix they just mentioned. So the location independent name that I just described. While the source contains a locator, where with locator I mean the identifier of a V6 interface. While for the reply, so the data, we just do the opposite. So we put the location independent name in the source address field and in the A locator in the destination of the field.
Clarification, is request response one packet? If you state your name, please. Run security. So a response must only fit in one packet.
Yes.
Okay.
Next. So the layer for header, so forget the UDP encapsulation, which is mostly for other things, but what you see here is a TCP header, just like we know it, but there's no TCP protocol in the endpoints. So we are using the TCP header to carry ICN semantics. So there's no TCP protocol at the two endpoints. It's just a header. It's just a container of fields that we will use differently. For the moment, the important header field that we need to consider here is the name suffix. So the one that I already just presented. The name suffix is an index that is pretty much a sequence number that is generated by the endpoints, by the producer endpoint that is segmenting the data, right? It's not necessarily a byte pipe, so this number can be generated in very different ways depending on the application. But it semantically carry index information about the segmentation made by the producer in the transport. Then there are other fields that we don't need for the moment to consider. Next. So a few security consideration about what I just said before about the data-centric philosophy in HSDN, which is every data path, even in the network layer, we need to authenticate and provide integrity to every single data packet, because as soon as you introduce location-independent communication, you don't know anymore, you cannot authenticate anymore the endpoints that is producing the data, because the data can be retrieved from multiple physical different endpoints. So you need a way to authenticate the association of the name prefix that is used for during the production phase by the data producer when the consumer fetches the data. And so this is visible in the packet, in the layer, in the network layer in two ways. Essentially, there is one incarnation of it, which is we basically insert the signature of a security envelope of the data packet inside of the packet, so that when the consumer fetches the data, can verify the signature just by knowing the public key of the producer and check and can perform the verification checks to verify the integrity by verifying the signature, but also the authenticity of the association of the name and the data that is actually available into the data packet. There is an optimization we call layer 4 manifest, which is very useful, which basically compresses this knowledge instead of doing this on a per packet basis in group of packets, where it's an optimization, but it is also actually the default function that we use in our software because it scales better. Essentially, it's a new protocol data unit that is carrying the series of different integrity hashes of each single packet in the block, plus the signature or manifest itself to provide the same authenticity and integrity features of the per packet basis security component. Next. So this is where we introduce a new node, a new IPv6 node, which is the HACN node, that does some additional forwarding processing with respect to the regular IPv6 router. Next slide. So we have, as I said, two endpoints. We have a consumer and a producer. Server. So in a client, you can have a consumer endpoint and a producer endpoint. In a server, you can have a consumer endpoint and a producer endpoint, depending if you're sending data or receiving data. But from a communication perspective, consider in this example one consumer endpoint and one producer endpoint. So this is so we have basically two different forwarding paths in HACN. One is the forwarding path followed by the request, and the other one is the forwarding path followed by the replies. And they follow different kind of semantics. So in this case, this is the interest path, so the request path, the forwarding path. So on the left-hand side, you see an ingress interface and a request packet coming in. And so the forwarding pipeline, so the router is very similar to a V6 router. The only difference is this new colored data structure, which is called packet cache, where we store PDUs for a certain amount of time, which are instrumental to perform the packet processing operations. So the first operation is to get the names. So as I said, the prefix and the full name out of the data packet. And this information is used, the full name is used to perform an exit match lookup in this packet cache to find either a reply or request matching this full name. If the interest packet, so if the request packet finds an exact match lookup, can reply with the data packet is sent back through the same input interface by performing a address translation operation into the reply by inverting the information that is in the request into the reply. So basically, we copy into the data into the reply destination address field the information contained in the source address field of the request. So, because remember, in the source address field of the request, we have a locator that is used by the data packet to flow back to the previous requester. So this is a first optimization. So that means that the data packet can be sent back to the consumer without going up to the producer if this has been temporarily cached in the neighbors of the consumer, for instance. If this doesn't happen, what happens is if no pending request is available in the router, the request is sent upstream, just like a regular IPv6 packet. So basically, you go through a V6 LPM lookup, and then you find the next hop route and send the packets upstream. When you send the packet upstream, you have another translation operation in the header, which is you store in the source address field of the request the locator of this of the chosen V6 interface. So that means that when you send a request upstream, the request records this information, so the locator information, into the source address field. It's a sort of proxy operation, so that the data will be able to reach back this very router in the route back to the consumers. Okay, next slide. So the data path is a little simpler. So as you can see, the request is basically is flowing upstream towards the producer or producers by using the V6 fib, just like a regular V6 router, plus the optimization of packet cache to reply in case the data is available locally. The data path is very different because the data path, we don't go through the V6 fib anymore. So there's no operation on LPM in the V6 fib, local fib. So in this case, we have on the right-hand side an ingress interface, and the data packet is flowing from right to left to the egress. And so the parser in the pipeline extracts the name prefix and the full name, and the lookup in the packet cache is essentially made to find one or multiple locators that are matching this the name in the data packet. So you can have one or many requests pending for the same full name, because you can have multiple consumers asking for the same thing as in multicast, for instance. So what happens is that the data packet that is flowing back is cloned through all the interfaces that are identified by the locator in the different pending requests, so that when the data packet is sent back, you perform another translate operation on the destination address field of the data packet, which is just like it is written. So for every single data packet, you store in the destination address field of the data packet the information that is currently available in the source address field of each pending request. Next slide. Of course, so the typical deployment of this kind of node is to be stored within an IPv6 network, and where you have regular V6 traffic. So in order to get HICN traffic, V6 traffic out of the network and process these spatial packets in a different way, you need to define a punting rule, which is basically related to the specific network configuration of your use case. Like you must be able to recognize that one, there is HICN traffic first, by looking at by identifying the existence of a location-independent name in the data packet, and second, you need to understand if this is a request or a reply, and depending on the first or the second case, you punt the traffic, you punt the packet towards one of the two forwarding paths that I just described. So there are many ways. This is still an open problem. So in our implementation, we have one way to do this based on classification and ACL rule, but can also be done in other ways. And this is open. Next slide. So a little bit about application support. As you can understand, this is not made to support TCP or UDP kind of traffic, but this is actually made. We're not describing in detail here for a new kind of a transport service running on top of this new forwarding mechanism. So I won't go through the detail, but essentially we have a new transport sitting on top of this request-to-reply semantics. We provide already in our implementation to natively a post-socket API as the one that is currently being worked out in the TAPS working group. And also for backward compatibility, a socket API, so traditional socket API. We provide two applications, two different kind of new sockets, types of socket types. One is the producer socket and one is the consumer socket. The producer socket, of course, is used to send the data. The consumer socket is used to fetch the data. And they are always unidirectional. So if you have a bidirectional communication, you basically open two sockets in the client or the server. So the producer socket performs the typical layer 4 operations, so like producer-consumer sockets, like segmentation and reassembly, plus additional operation like signature computation and integrity computation, and on the other end, signature verification, integrity verification, the consumer end. And of course, reassembly as usual. So you can have different types of socket, just like today, datagram, stream, but they go through the semantics of the forwarding path that I just described. Next slide. So to conclude, so the current architecture is a way to implement in V6 ICN semantics. So this has been done in the past in many ways as overlays in different philosophies. The The HACN approach is to go directly concurrently inside IPv6 instead of running on top of IPv6 or next to IPv6, replacing completely the network stack. So this is the chosen approach. So which turns out to be very useful for in many sense, deployments but also implementations. And so we have a prototype that we plan to open source in the following months, and for essentially support for two applications like HTTP and RTP in the first place.
Thank you very much. I'll speak loudly from this mic. I have a question, Juan Carlos Zúñiga, chair up. You're talking about the packet format layer 4, and you talk about reusing the TCP header by default. Still, you say this is not TCP traffic. So why is it that you want to reuse TCP and not suggest another transporter?
The reason why we decided to use TCP is essentially to go through middle boxes.
Cisco middle boxes?
No, I mean to have a high hit ratio in different networks. And also the TCP header it also carries semantically some of the things that you actually have in any kind of transfer, like segmentation information in the right place already. So it's been instrumental to implement actually all the features we needed for IEC and semantics in the transport. So that is one of the choices we've made for convenience, essentially.
Thanks. I see a big line, so please close it.
Gary Fairhurst, one of the people working on the TAPS architecture document. It's nice to mention TAPS, but everything I saw here looked like sockets, and these are very different concepts. Can you explain why you put TAPS on your slides?
Well, I misuse the term sockets with respect to the TAPS terminology, essentially because for historical reasons.
Tell me what in TAPS is relevant to what you talk.
Essentially, the producer socket is a buffer that binds to a prefix. And the prefix is a location-independent number. So which means that the producer socket, well, I continue to use the term socket, but the producer endpoint basically is nothing more than a buffer that binds a shared memory that binds to a V6 prefix that is available to a number of consumer sockets binding to the same prefix. So this is the high-level semantics of this endpoint.
Okay, I don't think I understand, but we can talk offline.
Carlos, this is to echo the question or comment about TCP from earlier. I worry that middle boxes will try to do things with TCP, assuming that the TCP header is, we're actually running a TCP algorithm on either end, and it'll just break. And not only that, but there'll be middle boxes that are like looking at TCP traffic to try to analyze it for attack patterns and things like that, and they might just block it because they think it's weird.
So we don't go through middle boxes doing connection trackers, no way. But in a way, we don't care. Like the assumption is not to go through any middle box, but to be able to deploy a protocol that is not that's not considered as an attack for even an IPv6 router. Like what we have is basically a datagram communication, connectionless. It's a connectionless communication, while some middle box they assumes by looking at the TCP header that you have a connection, a TCP connection, so they can modify the header fields for assuming some behavior, right? So we don't support that use case. Like anytime you have like a corporate firewall or the connection tracker, we go through those boxes by using tunneling between,
Well, why not just use UDP and only UDP?
UDP? You said UDP?
Yes.
We can also, well, the other example I showed you was using UDP as well.
Right, but I mean, I guess my point is saying TCP or UDP, not only does it complicate things because now you have an option, but TCP might just be broken. It restricts your possible use cases. If UDP is just as applicable, why not only use UDP?
I mean, I don't have any special choice. It's just as long as it works. The thing is, we need to carry semantics in our protocols that are that satisfy the architecture the architecture philosophy by carrying names inside the packet header. And for essentially the reason why we're using this header, we reuse these headers, is essentially to have the possibility to deploy this kind of protocols immediately. You may think about deploying a new header that would be very difficult to deploy in the short term, but maybe deployable in the long term. So it's a convenience for deployment reasons. So this is something that we can deploy today instead of redesigning a new header that would be hard to get deployed and go through deployments, actual deployment today, essentially.
No, I understand. I just don't understand why TCP and not just only UDP. Anyway, it's probably a moot point.
Because essentially because we found other problems with the UDP. So there's a trade-off. Like we cannot have 100% of the things that we wanted to have. So
Okay, maybe I missed you at that in the presentation. I didn't realize there was problems with UDP that were solved by TCP.
Again, for UDP, the main issue was in some deployment, there are rate policers that can just disturb the communication for some applications. And then what we've done is basically introducing a sort of UDP encapsulation, but it's almost used to just go through a given network. But it doesn't change the semantics of the protocol.
We're cutting the line of the 4 people about standing up now.
Arno Flink from Nokia. I missed the point. How do you resolve the destination name to this new address family? Do you go for each packet, the DNS server? How do you learn the destination? Especially when you say that the request response is 2 packets, 1 request and 1 response.
In the forwarding engine that I described, I don't go through the DNS.
Okay.
I just go through V6 LPM lookups in the local router. So which means that when the packet goes out from the consumer endpoint, it already has the location independent names in the destination address field, and then it goes through this.
But that's an address.
That's right.
Where does the...
That's the name. The name is the address. There's no other name as the address. The name is the address itself.
So the application provides that.
Exactly.
Okay.
So the name can be only 8 characters long, right?
Sorry, say it again?
The name has to fit in 64 bits then, right?
The name, the full name is, the full name is 128 bits plus the segmentation, the suffix. The name prefix is yes in 128 bits.
I had a question about how the packet forwarding works. You said the request is always 1 packet request, 1 packet response. But like a packet can only be, either 1500 bytes or 65K. So is there a limit of your chunk sizes then?
The response is basically NTU size. And the reply is NTU size. Like you go through the usual segmentation, NTU size segmentation. So the response is an IP packet.
So the maximum size of something that I can retrieve using this is 1K, 1.5K?
Or if you have other kind of segmentation, NTUs, yes. It depends on the NTU.
That means I have to index all the chunks of whatever I'm finding with...
That's right. That's right. If you look at the...
So what type of sizes can you accommodate? Is it just because 64 bits is really big number?
NTU sized. I mean, it's a...
Yeah, but it's never usul to fetch only 1K of data by itself, right? You have to, you're interested in
you
fetching
have
more.
one request. It's just like, if you look at the TCP stream, you basically have data that is sent, and the acknowledgement that is sent to say to the endpoints, I received the data. Here is exactly the opposite. I request the data to get I request the data, and then I get the data back.
But does that mean you can only do 1 packet per round trip?
That's right. Not per round trip, no.
So you have to stream. So you have to stream.
It's just like TCP. In TCP, you don't get a 1 packet per round trip.
So
You get the window, I hope, a window per round trip, right?
So next 2, please be brief. We're starting to run out of time.
David, let me make sure I understand what you described about use of TCP, that basically you're slapping enough of TCP header on this that it looks like TCP traffic to a really simple firewall that knows the TCP through and doesn't and drops all UDP. Is that correct?
I don't get the question.
Okay. What are you using TCP for? Does your traffic look like TCP to a firewall that's filtering on protocol number and using that to let TCP through and drop all UDP?
It looks like TCP traffic in the sense that you have a TCP header.
Okay,
But it's
that was a
not-
yes. What's your congestion control?
Okay, this is another question. There's not one. There are many, because what I described right here is just the network piece of it. As I said, there are several transport services. You can have reliable transport services, unreliable transport services. Let's take the example of a reliable transport services similar to TCP, what you can have in TCP, for instance. Then what happens is going to have a producer socket that is producing data and a consumer socket that is fetching data. So the consumer socket will be responsible to basically issues as many interests, so the request as required to get a full control retrieval of the data from the producer side. Okay, so the congestion control and flow control that you today perform in TCP on the sender side, in this case is performed on the consumer side by regulating the rates of the request sent toward the consumer side.
Got it. Okay, so there's no assurance that your traffic does TCP class congestion control. And let me just, okay, so let me issue a very blunt warning. The use of TCP to go to simple firewall, you may consider to be a feature. The security administrator of that firewall may consider that to be a bug and an attack vector. Be very careful what you're doing here.
That's right. That's a wanted feature, actually.
Like I said, the security administrator who runs that firewall and is using that firewall to solve a problem may not agree with what you just said. Be careful.
No, but that's right, because the point is, we don't want to say to the network administrator, hey, we are TCP traffic. We're not saying that.
No, but you're impersonating it to a firewall that is performing a security function to protect the network. You are on dangerous and shaky ground.
That's right. This is, I mean, this is true anytime you have a new transport protocol in the internet. Anytime you have LEDBAT deployed by BitTorrent and people scare about that because they say, well, this is new. And so you go through the IETF, which is why I'm here right now, to say, don't be afraid. There is something to be described in this framework so that you can understand what it is about.
Okay.
Gori is quickly interjecting that as a co-chair with David on the Transport and Services Working Group, you should come and talk there when you figured out how to do congestion control, because you do need to do that.
And this what we plan to do in the next IETF.
Excellent.
Perfect. Final question? Yeah, very quickly. Tommy Polly Apple. One more. So, I mean, first off, echoing the concerns around TCP, at least from my experience, I would bet that if you are on a network in which UDP has problems with the middle boxes, but your exotic TCP doesn't, that's probably going to be the minority of cases, and you're going to find a lot of places where that's going to break, and it's probably going to be better to just try to use UDP everywhere, because UDP state for things like quick are going to have to be more supported anyway. So if you're doing exotic stuff, do it over UDP. Then on the other side, regarding transport services and APIs and stuff, because I'm also working on that, I think there are a couple areas in which it does seem to relate, and I think this is an interesting experiment for that category of things. You definitely are trying to do an API that specifies whether or not you have reliability or unreliability. You are dealing with messages, not just streams or datagrams. You have like messages with interesting data in them. And then going forward, one of the things that we currently don't have in those APIs that we need to add is better support for things like multicast, in which you do have truly consumer and producer models. So I think that's going to be an area that we're going to be building upon. And I think actually that will fit much better to what you have than either sockets or what we currently have in specs today. Thank you very much. So please, if you think about feedback and respond on the mailing list, because we're out of time.
Sure.
Thanks.
The thing is that there's just about what Tommy said, just to, so the thing is that what we presented here touches many aspects, including the transport layer and the socket API. I still continue using the term socket API, but it's just, and there are many working groups where these things are considered. So this is the first step to disclose some of the work you've done at Cisco, and many other things will be disclosed in other working group, so that the full pictures will be more clear. But it cannot be done in one single shot, but many of the things that in the question that is raised today are absolutely normal, because the full picture is not clear in the single document. But there are many other documents coming in, and also software, where the full picture is more understandable.
Thank you very much. So, Ron, if you are brief, we would appreciate it. We know.
Okay, very fast. Okay, my name is Ron Bonica. My job is to be interesting enough to keep you away from your email for 5 minutes. Okay. And keep you awake. Okay, the title of the draft is IP Fragmentation Considered Fragile, and that's probably not thrilling to you. What will be thrilling is the last slide. In the last slide, we're going to make some recommendations. A, that people not develop new applications that rely on IP fragmentation because it's fragile. Also, it points out one application that is absolutely critical to the internet that relies heavily on IP fragmentation. There's a recommendation to those folks to maybe reconsider their reliance on IP fragmentation so that the world can migrate to IPv6 without too many more problems. Anyhow, what are we going to talk about? We're going to describe fragmentation really quickly. I'm going to assume most of you understand how it works already. We're going to describe how fragmentation reduces reliability, and we're going to talk about those recommendations. Okay, how does fragmentation work? Well, IPv4 fragmentation, defined in the IPv4 spec. Fragmentation is allowed at the source, and if you do not set the DF bit, fragmentation is allowed downstream. By contrast, in IPv6, fragmentation is allowed at the first fragment only. There is no DF bit. It's always assumed to be 1. Don't fragment downstream. There's something that IPv6 and IPv4 have in common. The upper layer header appears only in the first fragment. So when you fragment a packet, you'll see the upper layer header on fragment 1. You won't see it on any subsequent fragment. Now, for those of you who are thinking ahead, that's what makes it so fragile. Okay, thank you. When you're fragmenting at the source only, either if you're IPv6 or IPv4 with the DF bit set, the source has to do one of two things. It either has to refrain from sending packets that may be fragmented. In the case of IPv6, it has to refrain from sending packets that are less than 1280 bytes long, or it has to maintain a running estimate of the PMTU. Now, there are two ways to do this. One is with PMTUD, the other with PLPMTUD, and with some extensions by Gory Fairhurst that are mentioned here. It's not defined for UDP. Now, let's talk about how PMTUD works. The source does an initial estimate of the PMTU. That is equal to the MTU of the first hop. It then starts sending packets. If one of the packets is larger than the actual PMTU, a downstream node can't forward the packet. It drops the packet, sends an ICMP PTB back to the source. The source updates its PMTU estimate accordingly. This whole strategy relies on the intermediate node being able to get an ICMP PTB back to the source. PLPMTU works a little bit differently. Again, it produces an initial PMTU estimate. It sends probe packets of various sizes and relies on layer 4 acknowledgements. The source updates the PMTU accordingly. It doesn't rely on the ICMP PTB. It may accept them if it gets them, but if they're all lost, PLPMTUD still works. Now, why does fragmentation break things? Well, it's because that upper layer, that layer 4 header only appears in the first fragment. This will mess up load balancers. It will mess up firewalls, and it will mess up other middle boxes. Think for a minute about a firewall that is blocking all packets that except those that arrived on TCP port 80. Well, it's fine on the first fragment when it knows if the packet, by the way, this is a stateless firewall. It's fine if the first packet is on TCP port 80, Second packet, it has no idea that it was a TCP packet at all. The TCP header isn't in the second fragment. Okay, other problems with fragmentation. There are some well-known security vulnerabilities, overlapping fragment attacks, resource exhaustion attacks, and more. Then there is the possibility that your ICMP PTB is going to be lost. And there are many reasons why that happened. We won't jump into them. Probably the most common is common bugs in consumer CPE equipment, the router you buy at your favorite appliance store to put in your house. Also, many networks erroneously filter ICMP PTB message. So if you live in a world where you're trying to send packets bigger than 1280 and you're relying on PMTUD, it may not work so well. So there were some solutions to the problem. One solution is never send a packet that is likely to need fragmentation. And IPv6, never send a packet bigger than 1280. Then the transport layer, and by the way, that is the solution that most people rely on today. Next is transport layer solutions like PLPMTUD for TCP, or there's another work like it for UDP in process right now. Now, finally, the recommendations. The first recommendation is for application developers. Please do not develop more applications that rely on ICMP fragmentation. They're not likely to do so well in the world of IPv6 only. Second, for network operators, please don't filter those ICMP PDBs. And you should not deploy equipment that discards all packets that contain extension headers. We suspect that a good deal of that is deployed, and there is a RFC, whose number I can't remember, by Fernando Gant, that shows empirical evidence of that. But finally, there's a meta recommendation. There is one application, DNS, particularly with DNSSEC, that receives very small requests and answers with very large responses, responses that may be larger than 1280. Those responses, they can go either over UDP or TCP. Typically, they're over UDP. Performance gets pretty lousy when it's over TCP because you have to do all the connection setup stuff. So very typically, you get a DNS request over UDP. It comes in a single packet, and the response has to be fragmented. So we find when DNSSEC is deployed, as it should be, in networks where IPv6 is deployed, as it should be, we have a problem. So where do we go with this? We've had some good conversation with this on the 6-man mailing list. We presented it at the last IETF. I think we've had some conversation about it on this mailing list too. At this point, I'd like to ask for a call for adoption on the mailing list. That'll spur some more conversation. Maybe we go further, and the conversation begins now.
Lorenzo Caridi. So I agree with the statements of fact here that this stuff doesn't work. However, I fear that if we say don't do this, then developers who build networking applications are just going to say, "Oh, I know. I'm just going to do my own fragmentation," and they may or may not end up making the same mistakes that we've made. So it seems useful to say, look, if you really want to do fragmentation, do it like this, or don't do it unless you have to, but if you do have to do it, I don't know what the best practices are. Presumably, include a sequence number somewhere, because otherwise you don't know where the fragments are. Don't support overlapping fragments, right? There's been a history of security vulnerabilities, right? So, I don't think the recommendation can just be use TCP. It might be use TCP or QUIC, but, I feel that we have to say something,
I think you're right. It might be a good idea to add an appendix that says, here are your 3 options, use TCP, use QUIC, or if you're going to roll your own, here's kind of sort of what it should look like.
Do we anticipate lively discussion of what those 3 options might be, such that we might not ever agree on them?
Well, maybe if we say these are 3 and there might be 4, but we know these 3 work.
Repeating your line.
Great. Okay, I'm going fast again. obviously the problem exists, and obviously you're documenting it. The first recommendation is already BCP and RFC 8285.
Yes.
And the other ones are telling people who built equipment to now not do what they've done.
Yeah.
So that kind of leaves me wondering whether people will believe it.
Well, in fact, the draft does cite, I think it's RFC 5835 or something like that, or 5385, one of those. But in any event, it cites it, but the RFC was written years ago, and we're totally, it's as if it was never written. We're still dependent on fragmentation.
Yeah, no, the first line is 82885, which is BCP.
Yes, yes.
Yeah, so I mean, that's not years old. That's
Yeah,
quite
the first recommendation is rather redundant. This is more help on how to follow that recommendation.
Sorry, we've got the line.
Okay, Igor.
Hey, I'm completely in support of this thing because the reality is most of us large content providers do not allow fragmentation inbound, and we have tuned our kernels or applications in various ways to make sure that our packets stay, for some of us, below 1320, for others of us at 1280 or below, because otherwise we can't get it across the internet.
Thank you. David?
David Black, I support this draft also. Something else to think about adding. We use tunnels without even thinking about them. If I have a network in which the MTUs are all the same, and I throw a tunnel in the middle of the problem, what usually happens is I wind up fragmenting inside the tunnel as I tack another header on. So I think something that we very, very usefully do here would be a recipe for those who want tunnels to suggest how to go about doing it without having to resort to fragmentation. And this, of course, interacts with the tunnel strategies working group.
Yeah, and I think this is Appendix B.
Yep.
Yes, that's it. Thank you.
Thank you very much. So just 1 minute before Brian starts, a lot of discussion. We just want to get a feel from the group on accepting this work from Ron as a working group item. We just want to have a feel. So again, please hum if you think this is something that the group should adopt. Please hum. Please hum if you think this should not be adopted. It's mean for adoption with two sneezes. Yes. Thank you. Ryan.
Okay, this is definitely not up for adoption. It isn't even aimed at a particular working group. It's a bit of what we've started doing after thinking about various things that we've seen in the Anima working group and one or two other places about limited domains and internet protocols and how they interact. This is not about political or linguistic splintering of the internet. That's a politically correct version of the phrase we used in the 00 draft. And this is not about DNS. So, one fact, many types of limited domain are in fact appearing on the internet, or have been doing so for many years. Home networks, small office networks, vehicle networks, building services networks, SCADA networks, control networks of one kind or another, sensor networks, IoT edge networks are rumored. Whether they exist is another question. Enterprise networks and campus networks we've had for many, many years. Data centers, hosting centers, and some of those are distributed. They're not even located in one place. Network slicing is a popular topic in some places, CDNs, and there are other examples which people have brought to my attention this week already. So whatever we think about limited domains, they exist. There's lots and lots of places where you find the word domain used but not defined. Second fact, limited domain technologies are appearing. Differentiated services was specifically defined 20 years ago as a limited domain service. Network function virtualization is obviously limited to a domain. Service function chaining, yeah. NVO3 overlays are clearly limited to a real or virtual data center. Segment routing is very aggressively limited to a domain. autonomic networking has come up with something called the autonomic control plane, which is very specifically a secure limited domain. HomeNet has come up with HNCP. There's creative uses of IPv6. The flow label has been suggested for local use very often. Extension headers have been suggested for local use very often, including local insertion and deletion. And address bits have been used creatively. I wrote that before during the information-centric networking talk we just heard, which is an even more creative use of IPv6 address bits. And deterministic networking, DETnet work, is specifically scoped to limited domains. So people are designing this kind of technology, even though we don't actually know what a domain is. So the challenge that I see, in which led us to write this draft, is adopting the IETF as being that internet standards should be universal in scope and applicability. That's always been understood. You'll probably find it written down in a few places. But in the context of limited domains, some standards actually need to be limited in applicability. It matters that they're kept within the limited domain. The limited use requirement potentially adds complexity to the protocol. It isn't a way of simplifying stuff. And it certainly adds complexity to the security design, because the first question the security people ask is, how do you keep it inside? We also know inevitably a protocol intended for a particular scenario will be used elsewhere. That's a 30-year-old experience. So there's a challenge there, which is to reconcile these aspects, because at first sight they contradict each other and they interfere with each other. And yet, as I think I showed in the previous two slides, these things are happening. And it's the somewhat architectural question that it's very possibly an inter-area architectural question, but it may be broader than that. So what we think needs to be done is a bit more problem analysis, figuring out what the common aspects are of limited domains, even though they're very varied in type, and make the case that some protocols should be standardized to operate only within a limited domain boundary. I'm listening for shouts of burn the heretic, but I didn't hear any so far. But I think the reality is we have to do that. Such protocols are not required to operate across the internet as a whole. And for me, and showing the obvious deduction from that, is we need to define a limited domain boundary in some way, have methods of securely defining domain membership within that boundary. And that is intentionally where the document stops. The rest is TBD. And our main purpose this week is to garner interest in this topic. You can write to the authors, because our addresses are in the list, in the draft. And we'd love to take this conversation forward.
Okay, so I put myself on the line, and then I got it.
Kyle Rose. Actually, I was recently reading an RFC, or maybe it was a draft, I can't remember if it ever made it to RFC, was published a couple of years ago, talking about a TCP option for putting original addresses in the TCP header in case there was like a proxy or something involved. And that became of interest to me because I was looking at figuring out where a packet came from in a cloud provider network where there's many layers of NAT, load balancing, etc., that's hiding this information away from me. And ultimately, from reading this document, it was decided it was dumb because it wouldn't work on the wider internet. But it would have been perfectly fine in a controlled data center environment, which is where I wanted to use it. So it's unfortunate that it didn't really go anywhere, even though it was useful. So something like this, it makes perfect sense to me.
Okay, thank you. David Mark. Brian, so I shared the DiffServ adventure with you, and I think I'm with you on the slide all the way down to the very last bullet, where for some reason protocol is singular. Let me strongly suggest you meant plural, even if you didn't put it on the slide.
It's very possible.
And one of the reasons for saying that is that we actually do have one domain that we started with DiffServ, and it's been used a number of times since, and actually works quite well, which is the boundary of an operator's network or an administrative domain. I suggest that we actually do have the protocols that do a pretty good job of defining domain membership of that particular sort of domain in practice, but they're unlikely to be used for other sorts of domains.
Do you mean operate instead of interoperate?
No, I mean, they interoperate in the sense we normally mean, multiple independent implementations, but they only do that within the domain.
Because if you say interoperate there instead of operate, what it means is that I can have two almost identical protocols that differ in one constant, and they can't talk to each other.
I actually don't know the answer to that. I mean, there are subtleties in here, and you're pointing out that there are subtleties in here.
If you'd like to see an example of what Brian means by operate, please see RFC 7510 MPLS over UDP, which is quite clear that it will not operate in general cross-general infrastructure.
Right, and I guess I really don't understand what this even means, interoperate only. I mean, I think it's like saying we'll have two different languages that are almost the same. Maybe you mean operate.
Okay, I'll note that for the next clarification pass over the text.
And and so you're saying, okay, well, they only work in a domain boundary, and this is one of those things where it's like, well, it looks good on paper, and then, well, okay, so what if the domain boundary moves, and like, can they overlap, can they partition, and what does it mean then? I mean, generally, I think this is a way to be, I think it's a way to be lazy. We could say, well, yeah, we don't want to think about all these other use cases. We're going to this is one of the things that we hear a lot is like, this is never going to talk to the internet.
Well, that's what I tried to point out, but we know that's not true, right? And so if we're going to tackle this problem, we have to find a way of living with that fact of life.
Might I suggest that that one way of doing that is to make the failure mode absolute and irredeemable, right? So if you say, look, if you do this, it will just like totally fall over. That is actually a safe way of doing this. If it almost works, then that is a recipe, guarantee actually, of future hackery at the borders of these things, like NAT, for example.
Yeah, I agree with you actually. From very specific experience in trying to get Shim6 to work between New Zealand and Ireland, right, where, we could only get that AMN extension header through the network by hacking at both ends.
Okay, so Juan Carlos, just a quick one. I think that you are hearing that there's interest, but definitely it seems to me that you have to boil down a little bit more on what exactly you want to tackle. Because if you say there's an issue and we want to do something, it's easier than saying we don't want to do a whole bunch of other things.
Yep.
So probably it will be best to focus a little more and then.
Oh yeah, absolutely.
Thanks.
Ron Bonica, Juniper Network. Historically, the first time I shed blood over this problem was in 2003 in the L3 VPN working group, and the last time I shed blood over it was this morning. Given that long history of bloodshed, maybe this is a problem that needs to be addressed. I understand you're looking for a place to address it. It seems this working group is as good as any.
Well, there wasn't a random pick, but, I'd like to go a little bit further down the road of investigating the problem space before being convinced that it's here and not a purely security area problem.
I'm sure somebody pointed out to you maybe already that PVDs are also an example of domains. Maybe not exactly in the way that you mean, but sometimes they are just things that use internet technologies to reach non-internet services, non-internet reachable services.
And they actually be an example of overlapping domains, which is the problem that Ryan's mentioned.
Or an internally partitioned domain. And to that point, maybe, if this document goes forward, it might be good to have a section about fallacies of limited domains.
Yep. Certainly, you may write that section of the document. Thanks a lot, Brian. So, Eric? Yes.
So who cares about privacy? Some people are awake, okay. This is not intended for this working group. I don't know what to have this conversation, but that's what I'm trying to figure out. So this is, think about that and think about privacy. But I can do this fairly quickly. The draft is quite short, but it's a starting point to have some conversation. So, and I'm supposed to click forward. So we had the ideas BOF a couple of years back. There was an IETF BOF proposal this year, and there were all sort of discussions about, oh yeah, privacy, we should probably do something about that, but didn't get into a whole lot of detail. So I started thinking a bit about this and said, okay, let's write down some of this stuff and see and throw it out there and see what fruit comes back and see if there's, what did I do? Did I do that? There should only be one button forward. There are too many buttons. But the scope is really to think about what are the threats or issues in this space, not about solutions, right? And then see what is unique to this ID locator split. I'm assuming that everybody knows about ID locator split. If not, come and talk to me afterwards. My assumption here, and people have had slightly different assumptions in this space, but that you can have short-lived identifiers, ephemerals, right? And now you can say, okay, for those things, the privacy issues are less because they only live when they're only associated with one connection, session, whatever. But I think that you always want to have the ability of having some things that actually have some more unbound lifetime, some identifiers out there that maybe they're associated with your video streaming while you're watching a movie while you're wandering around, and you want to be able to keep that stuff. So the analysis here, it says, okay, let's assume that we have an identifier that's long-lived and see what are the privacy issues with that. And then we can always improve it by saying, okay, some traffic can have short-lived ephemeral identifiers as well. So that's sort of how I scope things. The draft talks a bit about why do we have ID locator split and why do we want to expose the locators. And fundamentally, it's about, in my mind, about latency bandwidth and sort of fault isolation, whatever, that I can keep local traffic local, I can minimize stretch from a routing perspective, and hence I want the cases when I want to be able to share those locators to make my traffic be as direct as possible. But, and this is sort of my initial short list, right? It's like, so what are the considerations about when you want to and not want to share that? Well, you might want to be able to share if a friend at the party or the party next door is streaming video, they already know that you're physically at the party, right? So do you have an issue with sharing your IP locator? Well, probably not, right? Because you're willing to share a GPS location. If you have a sort of constrained domain where you're saying, I want to use ID locators, but it's essentially as a form of scalable routing mechanism for this. It's fundamental about getting the packets to go more directly. Some of the conversations around applying this in 5G is of this ilk, right? Well, that's not that different from a privacy perspective than saying, I'm going to send around host routes in OSPF, right? Somebody that's part of that trust domain is going to be able to see the whole link state database and know where everything is. So doing that with ID locator, that doesn't change anything from a privacy perspective. It's really about defining the scope of that domain. And then, there are other cases like, well, somebody owns a bunch of trucks, right? Well, they want to be able to know the GPS locations of those trucks, having them be able to know the IP locators, that doesn't add any privacy issues. But these other cases when, okay, I leave this party, right? I don't want my friend to know what I'm doing the rest of my life, right? I want to be able to choose when they can see that. And I don't want, the trucking companies, competitors shouldn't be able to tell the IP locators of the trucks, right? So there's all of these things when the scope in time or who and when actually matters. Again, initial list, right? I think there's this one thing which is just about the location privacy. can you tell the IP locators of some device, some identifier? There's another one which is the mere fact of something having moved at a given point in time. If I can get a notification that this identifier moved from this room to the hallway, and I'm standing here watching, I can figure out who walked out the door or in the door at that point in time, right? You can correlate just those movement events with other information, and so there can actually be privacy threats around that mere event. So, short and sweet. There's some things that are not in the draft that Tom Herbert pointed out, that it's not all negative. If you have an ID locator split, and you're willing to use that to deploy some fixed points, basically some anchor points in the network, think, mobile IP home agents or whatever, you're saying that my locator is always going to be in Antarctica, no matter where in the world I am, right? And I can use this ID locator split to say, well, you can't watch me move, even less than today, because even when I'm going to go access, Google or whatever, I'm still ID located to Antarctica no matter where I am, right? That incurs more stretch, your lower performance, whatever, but there's trade-offs to do in this space. That's it. Who wants to contribute here or elsewhere? And if you have friends that are working on this stuff, this is not an internet area problem, it's an internet problem.
Juan Carlos Zúñiga, Chirjaraf. Yes, I'm interested in this work, and as you probably know, we are also working on this on the IEEE 802 side. So just last week we were talking about the exact same issues, just from the layer 2 point of view, and same problems apply: identifiers, locations, tracking, and how to not correlate them. So I think that this is very interesting, and in fact should ideally be taken from a broader point of view, considering all possible identifiers, because you can still correlate. The fact that we work here at layer 3 doesn't mean that the attacker or the threat cannot correlate with other identifiers on the stack. So yes, I would gladly be contributing, and in fact I think this can also help the IEEE work that we're doing with the IEEE 802E specification.
Okay,
thanks. Who's next? Richard?
Okay, hello. I'm Richard Patterson. I work for a quad play operator called Sky over in the UK. We have about 6 million subscribers on our fixed line network. Half of those are still using PPPoE, but the other half are making use of IPoE, or more simply just DHCP. This document adds additional functionality into those IPoE clients to hopefully mitigate some operational issues, or an operational issue that we are experiencing right now. The catalyst to write this draft was yet another discussion with a peer in the industry around the benefits of IPoE versus PPPoE. Now, we went through all of the obvious ones. There's less encapsulation overhead. It's simpler connection establishment. And most fixed line providers these days prefer to use port-based authentication, which makes CHAP superfluous. And then once you've gone through all that, you're probably going to be using DHCP-v6 over the top of this anyway, or at least I hope so. The one detriment that I couldn't argue against was its lack of sort of session state tracking, something that you get intrinsically with PPP and its keep alives. So in a PPPoE land, Both sides of the PPP session will send LCP echoes to the remote peer, which gives them visibility over that connectivity. So if that path, for whatever reason, temporarily fails, both sides have visibility and they can act accordingly. So the BNG can clear the DHCP lease, the lease that can tear down the subscriber session, and the CPE can restart its PPPoE client in order to trigger that authentication with Radius and so the BNG can allow that subscriber to re-authenticate and connect as quick as possible. In IPOE land, you don't really have that sort of session tracking at the moment. So what several BNG vendors have done, or taken it upon themselves to do, is implement their own kind of session tracking using ARP and neighbor discovery. Again, this allows the BNG to clear the DHCP lease and the subscriber session state, which can facilitate a customer to swap out their CPE or the router and to a new one without having to wait for the DHCP lease to expire. Now, in the IPOE land, if, for example, the reciprocate checking doesn't really exist yet, so in the CPE. So in a layer 2 metro access, if the BNG was to fail temporarily or was undergoing planned maintenance, or if that metro backhaul was migrated across to a different BNG, or if there is another network element in that path where it was behaving perhaps as a DHCP relay or a proxy and it keeps its own state, if that was to have issues, the CPE can be left with a stale DHCP lease for up to the lifetime of that lease. It still thinks it has a valid prefix delegation or an IPv4 address, and it would still be trying to forward packets via the BNG to the internet, and the BNG will just be dropping them on the floor. So what happens today is that after half of the lifetime, so in this example it's set to an hour, so after 30 minutes, the T1 timer would expire and the IPOE client would send a DHCP renew to try and renew that lease. The BNG no longer knows about this lease, so it just would typically silently discard that renew, as most BNGs would rely on a solicit or a discover to re-authenticate that subscriber. Now, the CPE will keep trying to do this renew, and BNG will keep on just ignoring it. And until such time as the DHCP lifetime of lease completely expires, the client will then enter the solicit and discovery phase, and BNG can then re-authenticate the subscriber and allow it to connect. So what we've done is we've broken this sort of draft down into 3 sections. So we have the parameters and the configuration thereof. We have the health check mechanisms themselves, and then we have the actions and behaviors to trigger once those health check fails. Do you want me to pause, Carol? Yep.
I just wanted to know if that behavior of the BNG not responding to a request is a bug according to the standard, and therefore could be argued that it needs to be fixed. You might have checked. Yeah, that's a bug, right?
So I guess it depends. So access nodes implementing LDRA would probably insert the option 82 and option 37 information into the renews as well. So technically the BNG could probably authenticate based on a renew. So I'll defer that to the vendors on whether they think their BNG should be able to authenticate on that. Yeah, arguably that could be a fix for vendors to implement. I'm not sure if it's a bug, because I'm not sure if there's anything that defines really that they should be authenticating on this or not. Yeah, so we've broken it down into those 3 sections. We'll start with the parameters and configuration. So the first one is the interval timer. Pretty obvious. This is going to be how frequently we will send the health check itself. The retry interval is then how frequently we'll send it after we've had a failed check. The limit being the number of consecutive failed attempts before we consider the health check failed, and then the behavior to trigger once that's failed. The passive flag, that allows, that forces actually this IPOE health check client to just passively check as opposed to sending probes. And then layer 2 would force a layer 2 check as opposed to using BFD echo that we prefer. And then the alternative target address field, that's what it says on the tin, use this IP instead of default. All these parameters can be signaled via, or should be signaled via DHCP within the lease that the health check these values pertain to. So an IPOE client might have multiple leases, in which case there'll be multiple health checks with different parameters going on simultaneously. We specify a new option for DHCP v4 and DHCP v6. Or you can locally configure these parameters as well. So you could have defaults on the CPE, or the user could manually override them via the UI, or you could push them down via TR69 or netconf. The health check mechanisms themselves, this draft specifies BFD echo at the moment. It's lightweight. It's just an IP UDP loopback. It uses the forwarding plane, so it has no impact on the control plane, unlike ARP-enabled discovery, or even the DHCP renews. And it has the added advantage of actually validating the DHCP lease as well, because the BNG would not forward it back to you if you didn't have that IP you're sending it to. If for whatever reason the client cannot use this BFD echo style health check, or it is forced to via that layer 2 flag, then it can use ARP and neighbor discovery for that health check probe. By default, the default gateway, but that's where the alternate target address comes into. And then again, if the IPv client cannot, or it is forced to not use that, it could passively monitor the ARP and neighbor cache totals on the host. All of these options would use the same parameter values. Now, once a health check has failed, this draft or this document specifies at the moment 4 different behaviors. The default 0 is renew. This is considered probably the softest approach. This would just send a renew back to the original server. So as per that previous slide, it may not necessarily work for all BNG vendors because they may not necessarily auth on renews. So, however, it is in line with Broadband Forum's TR146, as that's what they currently mention this thing should do. So then the next one is rebind behavior. This still doesn't solve that problem where you still require a solicit or a discover for authentication, but it is possibly beneficial for topologies where they may have multiple BNGs and another one could allow the subscriber to come online if the previous BNG has failed, for example. The third option, solicit, this is probably the one that I see being the most common. It's certainly the one that I see us using on our network. And this behavior skips the previous 2 phases and it goes straight to sending the solicit or discovery. It doesn't explicitly expire the lease, so the lease, the PD, will not be withdrawn from the LAN side. And ideally that prefix delegation will be mentioned in the IA request and hopefully get the same PD back again, so that it doesn't have to renumber. The fourth and final approach in this document at the moment is the expire and release. This is more of a scorched earth approach in the fact that it would immediately expire the lease. It will send out a DHCP release to the network to clear out any possible stale state within the network for any proxies or relays, and then it will move again to the solicit and discovery phase to allow reauthentication. And I think that's the end of the slides. Cool. No one's got to remote. Is that one?
Eric Klein, if you go back to, I think, 19.
Yes.
So actually, the Android phone actually uses a combination of 2 and 3. It will do passive observation of the neighbor cache, I mean, it can take action if it goes away, but if we do like a roam, a Wi-Fi roam or something like that, we'll also put the neighbor state, we'll also put the default gateway into probe state, and the kernel does its neighbor solicitation. And so you can even wait for things. So you can actually like use passive signals to trigger active neighbor monitoring. You can do both. I know you're talking about CVEs and stuff, but we have a similar philosophy anyway. Oh, cool. Thank you.
Last question.
Yeah. Security. So BFD is hard for some reason. Is it because of RPF or?
So I guess full BFD would be quite heavyweight, and then that probably would make that second point there irrelevant because it would actually require control plane processing on the BNG. Whereas BFD Echo, and I had a chat with Jeff from Juniper yesterday around this BFD Echo style. So we'll probably have to rename this because BFD Echo isn't literally true from this regard. So it would be a simple dumb IP UDP datagram IP addressed to yourself, so the BNG forwards it back to you. So BFD Echo style.
It creates RPF filters and so on. Generally speaking, I had a general comment about this. A couple of things. So first of all, you have 4 different recovery mechanisms, and you have like tunable parameters in DHCP. And how do you expect people to implement that correctly? When you have so many combinations, I mean, it's easy to say, okay, we've got like 16 combinations of ways to do this, and we're going to club our vendors if they get any of them wrong. But it seems easier to say, well, we only have one way to do this, and then we'll club them if they get it wrong. It's sort of more likely to result in success, I feel. So I would think, I mean, while it looks good to have lots of options, you might be able to gain consensus on the draft more easily. It's like if you chop them down, it's actually going to be more reliable.
Yeah, thank you for that advice. I have been told to just keep it simple. So yeah, going back to the behaviors, I could be convinced easily to drop the first 2 because I don't believe that they would be too useful, certainly not in my network, and I'm not sure what other networks they would be useful. So again, based on community feedback, I wouldn't be averse to dropping those first 2 approaches. Okay. Now I know most of this discussions happen on V6 Ops or offline even, so I'd still probably like to ask the chairs if they think this working group is appropriate for this, or if you'd like to consider perhaps a call for adoption.
Well, right now, we encourage you definitely to keep discussing on the mailing list first, and then depending on the interest of the group, we can.
Do you think the working group itself is the appropriate place for something like this?
Yes.
Cool. Right, thank you.
So,
Okay, this is an update on multi-access management services that we presented, I think, 2 years ago. And since then, we tried to onboard this to Banana Working Group, but that didn't materialize. So how we are now positioning the work is that we are an individual submission track. We are happy to bring it to any work package, work group that would like to work on the topic. But what the multi-access management service is about, it is a framework for configuring and selecting protocols for multi-access use cases. It has a control plane, which is application level control plane, and then it has means of aggregating user planes. The control plane itself is agnostic of the used tunneling protocols or user plane protocols like multi-path TCP. What it does, it discovers and selects network side proxies, configures the paths independently for uplink and downlink, and is able to adapt the scheduling based on network conditions using the path measurements and analytics. The MAMS concept is under discussions in a number of standardization and industry forums. The first one being 3GPP, where there is a study on access traffic steering, switching, and splitting. It's there part of solution one. In Wireless Broadband Alliance, it is part of the discussions on unlicensed integration with 5G networks. In Small Cell Forum, it is part of the discussions of integrating LTE 5G with Wi-Fi. In ETSI, it's part of the requirements, and through the use case, it identified use cases of multi-access, and it's also part of the Wi-Fi Alliance discussions of Wi-Fi cellular integration. So what the framework does, as I said, that there's the element of control plane, which is application level, and for that we have, of course, the applications that are using this control plane. We have network connection manager, which is sitting in the network. It does not need to be at the access network. It can be in the enterprise network. An element that is the topology and the connections, and then, of course, the counterpart, the client connection manager, which typically sits in the handset or the host. And then it has the proxies that are configured according to the messaging exchanged over the control plane. And in the host side, we of course have these independent IP protocols. So as I said, the control messaging is WebSocket based, it's a JSON coded, TLS secured. The user plane has means of aggregating multiple different tunneling protocols or multiple TCP. In the case of multiple TCP, the convergence layer could be zero, so it looks directly into multiple TCP. The use cases that are benefiting from MOMS are, of course, the integration of LTE and Wi-Fi with enterprises and public venues, because of the control point can be at the enterprise side. It is beneficial for introduction hotspots and small cells in the emerging 5G deployments, and then it is useful for reducing for existing fixed line assets and joint traffic steering across multiple networks. So this was just to inform the community that there is a draft, that work is ongoing, and if you are interested, please comment, read the draft.
Thank you very much. So we're 2 minutes past the time, but if anybody has any final remarks. Okay. Seeing none, thank you very much. Thanks, everyone. If you have not signed the blue sheets, at least I see one here in front, so please do sign them. Thank you very much.